Every day, billions of engines perform a silent transformation. You pour a liquid into a tank, and moments later, that fluid provides enough force to move a car, propel a massive container ship, or generate the thrust required to lift a rocket off a launch pad. Fuel is a dense reservoir of solar energy. Millions of years ago, ancient plants absorbed sunlight through photosynthesis. Over geological time, that energy was buried and compressed into the carbon and hydrogen bonds we refine today. A tank of gasoline acts as a highly compressed chemical battery, holding millions of years of solar history in a state ready to be unleashed. If fuel contains this much energy, why can't we simply ignite a puddle of it on the ground and use the fire to push a vehicle forward? As this simulation shows, naturally occurring combustion is chaotic. It releases its energy as a rapidly expanding sphere, pushing with equal force in every direction at once. To create motion, we must cage this expansion. An engine exists to trap that multi-directional chaos and force it to move in a single, useful path. This starts with the cylinder and the piston. By enclosing the fuel inside a heavy metal chamber, the engine ensures that this energy has nowhere to go but against the surface of a moving piston. During intake, the piston moves downward, letting atmospheric pressure push air and fuel into the void. To maximize the burn, the piston rises, crowding molecules into a tiny space. This intense compression raises the temperature and pressure, making the mixture far more reactive. Diesel engines take this process even further, squeezing the air so tightly that the resulting heat causes the fuel to ignite automatically, without needing a spark plug. In a standard engine, a spark ignites the mixture. The gases expand, forcing the piston down, the only moment power is actually generated. Finally, the piston rises again to sweep the spent waste gases out of the exhaust valve. This sequence is the exact point where the potential energy of chemical bonds becomes the kinetic force of a moving piston. But there is a mechanical disconnect. The piston moves up and down, while wheels must spin in circles. The crankshaft solves this by linking the piston to a rotating offset. As the piston pushes down, it forces the crankshaft to turn, converting linear movement into rotational force. This works just like a cyclist's legs. Your knees move up and down, but pedals and crank arms translate that vertical effort into the circular motion of the chainring. The crankshaft ensures that the violent, sudden push of the power stroke is captured and turned into the continuous spin that moves the vehicle. If we used only one cylinder, the ride would be extremely jerky. The engine would only provide a push for 1/4 of its cycle, leaving the vehicle to coast through the other 3. To solve this, engineers combine multiple cylinders, usually 4, 6, or 8, into a single engine block. By staggering each cylinder's timing, engineers ensure that as one piston finishes its power stroke, another begins. This offset timing fills delivery gaps, turning individual kicks into a constant, uninterrupted stream of torque against the crankshaft. This coordination transforms a sequence of isolated explosions into the smooth, predictable rotation we feel in a modern car. Even with this mechanical precision, engines still fail to transfer a large portion of the fuel's energy to the wheels. Nature dictates that much of the energy from combustion is lost as waste heat. It escapes through the exhaust or radiates into the metal parts of the engine itself. Radiators and cooling systems are essential for survival. Without them, the engine would absorb so much of its own thermal energy that the metal components would eventually warp or melt. Within every second of driving, a massive chain of events occurs. Chemical energy becomes heat. Heat creates pressure. Pressure generates force, and force becomes motion. When you start your car, you are witnessing the release of sunlight captured millions of years ago, triggered by thousands of timed explosions every minute. The internal combustion engine operates by constraining chaos. It traps a violent, multi-directional expansion and forces it into a singular, productive path. What complex machine should we decode next? Let us know in the comments, and subscribe to explore the hidden science behind the world around you.